Hello everyone, and welcome to today's webinar on CFD for electronics packaging. Glad you joined us today. My name is David. I'm CEO and co-founder here of SimScale. And before we dive into the topic today, I quickly wanted to get some technical things out of the way. You should be able to hear me by now. We're using GoToMeeting or GoToWebinar to stream this webinar today. And if you could, there's a little feature on GoToWebinar where you can ask questions, and there's also a feature that says raise your hand. And so if you could quickly raise your hand right now, if you can hear me, that would be fantastic. Then I know everything works. I can see a lot of hands. Great, that works. Thank you very much. Also, GoToWebinar allows you to ask questions. So at any point during the webinar, just type in the question you have, and I'll regularly check on whether or not there's an urgent question. By the end of the webinar, I'll try to cover all of them. If I can't cover all of them, I'll try to follow up by email. There's also an active forum on SimScale where you can ask more questions. All right, then let's get started. To quickly put the importance of today's topic in context, we're seeing such electronics or cooling applications, thermal management simulations on SimScale a lot. So we're seeing on a daily basis, new users, new customers being interested in running such thermal analysis of some sort of enclosure. Sometimes they are sealed, sometimes they're open, all sorts of different cooling strategies. And I think the overall context is all the time that many products get equipped with semiconductors, equipped with some sort of sensors that produce heat, that a couple of years ago or a decade ago didn't have any semiconductors in there, right? And the common denominator is the Internet of Things, right? That there's many products being equipped with sensors, and all of them produce heat. And now products where a decade ago it was not necessary to manage any, thermal or to do any thermal management of these products, meanwhile it is, right? And this is a little chart that I think shows well that this trend is here to stay, right? That more and more industries, more and more consumer products, more and more things we see around us will be equipped with semiconductors, and all of them will produce heat, and that's going to be managed, right? That wants to be managed, and ultimately that's on us as engineers, right, to manage that, to exactly prevent this, right? A couple of photos indicating when things go wrong. What we'll do today is a hands-on design scenario. Let's quickly also manage some expectations for the session today. We call these webinars editorial demos, right? Where we show in 20 minutes. I'm shooting for 20 minutes today. Let's see if I can stick within that time frame. Where we show in 20 minutes a super fast walkthrough through a project that has been completed on SimScale from a particular industry, right? So what we'll see today is an example application of where an electronics packaging, an electronics enclosure has been simulated on SimScale with regard to whether or not the cooling efficiency is good enough, right? Whether or not the chips that are in this enclosure maintain a sufficiently low temperature for normal operations, right? That's what we're going to look at today. I'll try to give you a feeling for how SimScale looks and feels like, how the workflow generally looks like, but we won't go into a lot of detail, right? We won't go a lot into, CAD preparation, physics, CFD theory, etc. This is not what this is about today. But the good news is that the exact project we're going to look at today is available as a public project on SimScale. So if you're interested in seeing the details, how the simulation was set up, and want to ask questions about that, feel free to do so afterwards, right? And dig into this project and see its details. All right. The design scenario today we're looking at is this little piece of high power density electronics. So we've got a PCB board at the bottom, and we've got, let me use the drawings over here. okay, so we've got the board here at the bottom, right? And then we have a bunch of semiconductors around, right? Here's a CPU that you can see here where we've got a heatsink on top of it. We've got 4 additional boards, right? 1, 2, 3, 4 over here, where we have a bunch of capacitors, a bunch of other chips on it. We've got more chips here, right? Like rather a very, very, dense packaging of different electronic components that shall be put into an enclosure, right? And let's click once forward. And so all or many of these components produce heat, right? That have a certain heat loss. The CPU has the highest, right? Where we're looking at 30 watts heat loss, and then there's a bunch of components around it. So we've got another 10 watts over here. So each of these blue chips is losing 10 watts in heat, or emitting 10 watts of heat. We've got a transformer with 6. We've got all these little blue components that have 5 watts. So we've got a ton of wattage in here, a ton of power that is being put into, that is being lost as heat by all of these components. And now we want to put this thing into an enclosure, and we're asking ourselves as engineers, okay, all of these chips and all of these electronic components should maintain a sufficiently low temperature to operate normally, right? To reduce the risk of overheating and therefore shutting down. And that's what we want to validate, right? How does the electronics enclosure needs to look like? How does the cooling strategy needs to look like for sufficient cooling? And that's basically, let me quickly erase that. There you go. And so here we can see this board with all its components on it in the context of the enclosure, right? And so we've got, you can see it already here on the left, we've got these 2 little circles. So you can already see that we're gonna use a forced convection strategy. So instead of, having natural convection in here, what we choose as engineers in an intuitive move or intuitive decision is we're going to use 2 fans that we're placing here on the left, and we have the outlets on the right here, right? So forced convection cooling strategy. This device is going to operate under normal room condition. So we're assuming we're bringing in fresh air supply at 20 degrees Celsius and have an open outlet over here. And so the air is going to move across all of these components. We're hoping that it takes enough waste heat with it and moves it out of the enclosure to maintain a sufficiently low temperature. And so the question is, will that work, right? And that's what we're trying to answer today. So to sum this up, we've got the cooling strategy, we've got all of these components producing heat, and a summary, as you can see, that's why we're calling it a high power density electronics component, right? So we've got north of 600 watts total power inside this enclosure. We've got a certain cabinet volume of this enclosure that gives us a certain power density. And the main design constraint we're having is we're trying to keep all of these devices, all of these electronic components below a certain temperature. In today's session, or in today's scenario, we're looking to maintain 50 degrees Celsius, right? Or keeping all chips below 50 degrees Celsius. We chose this CAD model or this application because it's very it's a good representation of many applications we're seeing of many customers that are running similar things on SimScale. It might be a particularly extreme scenario, right, with lots of wattage in here, with lots of power in here, but this is the complexity, the number of parts, etc. we oftentimes see, and so it shall serve as a good demo for today. What we see then customers oftentimes doing is, obviously, and that's what we're going to do today, fan selection. So how much airflow, how much fresh air supply do the fans need to provide for sufficient cooling? Another thing, what we won't look at today is fan placement, right? And then obviously component placement, right? What type of heatsink, how do I put these boards in here, where do I put the chips, etc., that ultimately I have sufficient cooling going on inside the cabinet. All right, just a few words. Obviously, today we're gonna use SimScale to do that. There's many different thermal simulation packages out there. So why did we decide, to build another one? And at the core of what we're trying to do with SimScale is we're trying to provide a simulation solution that allows every engineer and every designer to leverage simulation, and not just the ones that are well equipped in terms of budget, well equipped in terms of hardware, and educated on these tools. And at the core of what we're doing, we want simulation to become accessible, meaning no hardware, no software. Right? We're going to see today it's a web application. I know in the audience are people that already are using SimScale, but some of them don't, and so there's no install. You simply open up simscale.com, and on simscale.com you can run your simulations inside a web browser. Second thing is cost efficiency. So SimScale starts completely for free. There's a free community plan where you can simulate everything for free. You have all features, you have computing power, but if you don't pay for it, simulation projects are publicly accessible. And then last but not least, the know-how component. The beauty of SimScale is that everything is entirely centralized, right? So all users, all data lives in the same stack, right? And so there's new ways how people can collaborate, right? So we're going to see later that there's a live chat with our support team. We've got an application engineering team here on staff that helps our users to navigate through simulation projects. Customers can collaborate within their company on SimScale in real time, et cetera, et cetera. There's more mechanisms that make it easier for people to get started. That's how the workflow looks like. We can see here a conjugate heat transfer analysis being done on SimScale. So you can see on the left, you bring in your CAD model from the CAD system of your choice. We're supporting multiple native formats, also general exchange formats such as STEP or IGES. You bring it in, and then you can interact with it in 3D, just as you would on a desktop application. And then you have inside SimScale everything you need to set up a simulation, run it in the cloud, and then later on analyze the results. A few general notes. So today we're going to mainly do thermal management, right? Thermal analysis. And there you have multiple options in SimScale. So you can run conductive heat transfer only. So only looking at heat transfer inside solids, which we can see in the top right. This is a gearbox housing where only heat transfer has been analyzed inside the solid, right? You can look at convective heat transfer only. That you can see, for example, in the lower right, a coolant water flow. So we're only looking at heat transfer inside the fluid phase. And then what we're going to look at today is a coupled heat transfer analysis, right? Coupled between conduction and convection. And that's, for example, the two applications on the left, a heat exchanger in the lower right, an electronics cabinet, where we're looking at conductive heat transfer inside the solid components, and then convective heat transfer inside the air, right? And the heat transfer coefficient between between solid and fluid is being computed on the fly. And that's what we're going to look at today, right? It's typically used in electronics cooling applications. Beyond that, you can see on the right, there's more things you can do, but that just gives you sort of an overview what's possible with SimScale. Beyond that, SimScale is a general purpose simulation tool. So we're going to use today a finite volume method for this conjugate heat transfer analysis. But besides finite volume, there's also finite element-based solvers in SimScale. So you can see here in the top right a nonlinear analysis of an assembly. So we're having a fully fledged structural mechanics simulation suite in there as well, and a bunch of more exotic simulation or analysis types as well that you can see here in the lower right. All right, enough talk. Let's see something in action. And what we'll do, before we jump into SimScale, what we'll do is we'll run a conjugate heat transfer analysis of this electronics cabinet. So what you see right now in a transparently colored here is basically where air is, right? So inside this air domain, we're simulating a convective heat transfer. So the air is being moved in from the left through the fans, and then it flows around these solid components, takes on heat or takes off heat from these solid components and moves it out, right? While at the same time, we're applying different heat sources, the wattages we've seen in the beginning, right? The watt values we've seen in the beginning on these solid components, and we're looking at conductive heat transfer in there, and then at the interface between the solid and the fluid component, heat is being transferred into the fluid region and is being then taken away by air. That's sort of what we're looking at, right? And to give a quick preview, here on the right, you can see all solid components color-coded in as temperature, right? We're gonna analyze that in a second in more detail, and then we can see the air being color-coded by velocity, so how the air is moving around the solid components. We're gonna look at the results in a second in more detail. All right, so let me quickly move away from the slides and jump on a web browser. Okay, as mentioned before, for the people that do not yet have a SimScale account, SimScale is a web application. So you go to simscale.com. In the top right, you can see the sign up button where you can create an account. It's going to take you 2 minutes. And once you have an account, you can simply log into that. American keyboard, sorry for that. And once you've logged in, you can basically, you can see public projects, you can see private projects, so you have access to the full application inside here. And so I prepared already this project for you. And as I said, we'll not dive into the details of this project, you know, how to set it up and into the theory behind it, etc. Not at all. I just want you to get a feeling for how SimScale looks and feels. So this is the CAD model we brought in. In that case, it was modeled in a cloud CAD software, and we brought it in without it ever touching my hard drive, right? And so we can see it's let's check. It's 126 solid assembly. So we've got the CPU down here, right? We've got our components over here. We've got more chips there, so that's exactly the PCB we were looking at, right? And for you to get a feeling for then how the next workflow is that you typically start by generating a computational mesh for it. Depending on, you know, if you're looking at a finite volume or a finite element solver, you have different mesh generation methods available. And how this looks like is now we're loading there, just like, you know, without going here into the details, zooming in. So you can see that the CAD model has been discretized into many different, into many small cells that's going to be used in the simulation, right? You can see here also the inner components, etc. And as a next step, what you'll do is you'll set up the physics of the simulation. And also here, I want to be brief. So we created a simulation over here. We chose the conjugate heat transfer analysis as an analysis type. And what you then do is then you go from top to bottom, work your way through the simulation setup. Everything that's blue is optional. Everything that's green is already defined, and everything that's red is still needs to be defined, right? And I'm just going to look at the most interesting things. One interesting thing is obviously the material assignment. So where do I have air? Where do I have my semiconductors? Let's give the model another few seconds to load. We're looking at for the CFD folks among you. We're looking at, I think, roughly 13 million cells here that are currently being rendered. And so we've defined basically different materials. In this case here, we are looking at air. And once the model is loaded, we're going to see where air is applied, right? So this is our flow volume, everything that has been made blue. And then we can click on the other materials and see where this is assigned, right? So we've got tin, we've got copper, we've got silicon, we've got PCB material. And down here we can see to which solid this was applied, and you could add more materials. You have the material parameters that characterize your material over here. And then next and more interesting, let's quickly see. Now the model is fully loaded, and now we can see already a visualization of this, right? So you can see that these are the boards, right? The PCB board. These are the silicon points, then the transformer out of copper, and we've got tin over here. And then the more interesting things now come down here, the boundary conditions. We're looking at a fan inlet, a pressure outlet, and some fixed temperatures. And the most interesting part is down here, the heat sources, right? So we applied these heat flux values, the wattages we've looked at before, right, at these values. And let me quickly do the following. I'll quickly hide these faces. Let's hide the entire solid. There you go. So you can see that we've defined the different wattages here, right? So we've said we've got 10 watts. These guys, we've got the small capacitors, each of them 2 watts. We've got the medium capacitors over here, right? And that's how you define these heat sources. It's as easy as that, right? You bring them in like that, and you can see how the simulation was set up. And then the last piece is that you run it. In that case, on SimScale, you've got all the computing power you need. So you choose the amount of cores you would like to run this simulation on and kick things off then in the last step. You've got direct feedback while your simulation job is running. This one has been already carried out. You can see it took around about 8 hours to compute, and that's sort of, just for you a feeling for how the setup looks like. And what we'll do next is sort of we'll save the entire simulation analysis, how you do post-processing, and directly look at some final results because we're running short on time here. What you'll get out of a simulation result on SimScale, out of such an analysis, is you get all the result values, meaning temperatures, velocities, pressures, turbulent quantities, in all, within the solids and within your fluid regions. Obviously, velocity and pressure only in the fluid regions. And this is now an animation of a slice view through, starting from the fans. You can see here in the top left we have the 2 fans, right, bringing in fresh air, and then how this slice moves through, right? And we can see now in each slice how the velocity looks like, right? A bit further down, so we can see that it's going through the channels being formed by these 4 PCB boards, down here through the heatsink, and then leaving again through the slots here at the bottom, right? That gives you a qualitative feeling for how the air movement in here looks like. And then similarly that way, right? So we can see it's a color coding of this initial setup that we wanted to look at. So we can see already, see at the very back here, we have not a lot of movement down here, right? We can also see that, let me quickly draw something, and it's going to be important in a second. We can also see that here we have some blue areas where not a lot of air movement is going on, right? And we can see in a second what's going to happen there. Here it's actually okay, right? Here it looks okay, but we can already get a feeling for how our air moves through this enclosure. Let me quickly erase that. All right, just finishing up this video. All right, and now digging a bit deeper into this. This is now a cut section of this initial setup, of the initial fan choice, right? Intuitively, we said, hey, that's the fan we normally take, so let's just use that one. On the left, we can see velocity color coding here. And as I just already had highlighted here, we can see we've got blue stuff going on here, right? So we see that there's some there might be some insufficient cooling over here. We'll see in a second, right? We've got lots of blue stuff here, but actually we don't care because not a lot of heat is being generated there. Also back here, there's not a lot of movement going on. But again, we probably don't care because we don't have, you know, a lot of heat loss over there. So that might be fine. Let's erase that and move on. And now here we put this velocity cut section through the velocity field over a temperature plot of the components. And there you immediately can see it, right? We've got temperature being plotted at 60 degrees Celsius. So red is 60 degrees Celsius. And so we said we want to shoot for 50, right? And we can see that the capacitors here on the left are actually fine. So we're good here. We're green, that looks okay. But here on the right, we can see that due to the fact that not a lot of air is going there, we've got low velocities there, that might be the reason for these guys to heat up more than we would like them to be, right? Removing the cut section of the velocity and just looking at these temperatures, here we can see it very clearly, right, that we've got some semiconductors that heat up too high in these regions. And that's something we might want to take care of, right? Another visualization, again, highlighting it in pretty clearly, right? We've got not a lot of air being moved there because of the larger components that's in front of it, leading to the fact that they're convectively insufficiently cooled and getting too hot by that. And that's what we want to take care of, right? And that's the next step, right? So what do you do with simulation? You use the insights, and without having built a prototype, without having invested any time into manufacturing, we're going to build a prototype. We can derive design decisions to get to a better design. And to make this a very crisp demo, you know, and to stick to the 20 minutes, we'll do it very simple, right? Today we only look at different fan choices. Customers are doing all sorts of things, right? I could think about maybe moving these components to another place where they're better cooled, or maybe changing the fan placement up there, etc. But we want to keep things very simple. And what we'll simply do is we're going to use more different fans. We're going to use a fan that moves more air into the cabinet. We're looking at the exact same cabinet, at the exact same PCB board, and we're just moving in more air. So we're looking at 0.3 meters, 0.6 meters, and then 1.0 meters per second in fan 3. So simply we're going to move more air through it. And we want to look at the effects that this more air movement has at the temperature of our semiconductors. And that's what we've done. So you basically run on SimScale the same simulation 3 times with different boundary conditions, right? So the manual time here is very low, and you're going to get these results. And so we can see what we expect, right? Same velocity color coding for all of these 3 plots. And so we can see qualitatively the velocity field. So we're moving in air from the top right down here. Qualitatively, it looks very similar, and on the right we can see that simply we'll push more air through. So let's take a look at this, if this is now sufficiently cooled. And yes, it is, right? So simply by the fact that we're moving more air through, we have more convective cooling happening at these capacitors where we had problems initially, and can see that we're going to get better or lower temperatures there. So the fan 3 has moved the temperatures, the peak temperatures of our semiconductors down by more than, or by roughly 20% below the 50 degrees Celsius that we shot for, right? And that's basically one simulation ran with 3 different boundary conditions gives you these design insights, right? All of that done in a web browser. So to sort of sum up this quick 20-minute demo, what we've done is we've started with an intuitive sort of what we as an engineer would say, okay, that's what we would intuitively choose in terms of a fan placement, in terms of a component placement, and in terms of a fan selection. We run the analysis to find out that some of our chips go up to 60 degrees Celsius inside the cabinet. And let's assume in this design scenario, we wanted to shoot for below 50. Right? And so we quickly iterated a bit further. In that case, we've chosen other fans. In other scenarios, we might have, chosen a different component placement, you name it. And we run the analysis again and see, okay, now we are sufficiently cooled. That's a fan we should probably go for. Overall, the setup of this, since in SimScale there's quite some automation built into, automatic detection between of interfaces. There's lots of automatic meshing being built in SimScale. So the manual time is a couple of hours in this case. Computing time, you've seen it, it was north of 500 minutes. So the computing time I'm waiting for my simulation to be done is roughly 8 hours, a little bit more. I can run all 3 simulations in parallel because of it's a cloud-based application. And bottom line, it was roughly 400 core hours that we've used, right? Because we ran it on 16 core machines. Yeah, and ultimately, it's often the benefits I'm getting as an engineer is, or that we see our customers getting, is that without going onto a testing phase, building a prototype, etc., you can just based on your CAD data get the design insights you need to move forward with confidence, right? And that's ultimately oftentimes the case why customers choose to use simulation. To wrap this up, and I almost got the 20 minutes. To wrap this up, don't take my word for it, right? Test it yourself. The beauty of SimScale is that you can just sign up yourself on simscale.com. You can either get in touch with us and we're happy to give you an individual demo and walk you through into more detail, but you can also simply go with a community plan and test it yourself, right? And give it a spin yourself. There's many public projects around electronics components, electronics cooling, all sorts of cooling applications. So make sure to check out the public projects and give it a spin yourself. And with that, I say thank you for the attention today, and let's see if there's some questions we should dig into. All right, so there's probably too many questions that we can cover in today's sessions, but I'm gonna try to select a few of them that we at least cover some of them. So one registrant asks if the heat flux definition is actually a watt per unit volume for the component. So there's different ways how you can bring in a heat flux definition, and yes, there's also the option to choose heat flux per unit volume. But in that case, it was an absolute value for the watt that is being applied to the solid where you apply it to. But there's many different ways. I mean, we've got also customers today, we looked at electronics cooling. We've got also lots of customers that are using similar physics in, for example, in the HVAC sector, right? And there's oftentimes other boundary conditions or other types of heat sources being used. If there's a particular way how you would like to apply a heat flux, let us know, right? We're always looking for feedback and see and learn about ways that we haven't covered. So let us know. So one user asked, or one registrant asked, the simulation took 8 hours on SimScale, and I just wonder how long it would take with another simulation software. I mean, it's hard to answer that question. I think you're right. It could. We do run benchmarks, but obviously not exactly for that simulation, so I don't have any reference values there. I think the one unique thing about SimScale is that you have free choice over the size of the computer you want to use, right? So this simulation today, I think we carried it out on 16 cores, but there's larger instances also available on SimScale. So the beauty is that hardware, you have unlimited access to hardware, right? And you can just choose the machine you want. But you're right, if you would use another simulation software on a similar system, it would come down to a benchmark, right? Which one is faster? Yeah, there's so many more questions. I couldn't find one that we could answer in a quick answer right now. So what I would suggest is I'll try to follow up on these questions in a one-on-one setting, and for the ones that might have still questions, I really encourage you. We have a very active forum on SimScale, so I'd encourage you to go to simscale.com/forum and take part in the discussion there. Right. At the same time, feel free to reach out to me directly. My email address you can see here in the on this slide if you have an urgent question, and if I'm not able to answer the question, I'll find an engineer here at SimScale that can. So feel free to reach out. So with that, I would wrap up this session today. Again, thank you so much for joining, and I'll hope to see you around on the SimScale platform shortly. Have a great day. Take care. Bye-bye.